Now we'll solve a standing wave example problem, and here we are asked, we're told the string oscillates according to this equation and asked to solve for its amplitude, speed of the waves that create the standing wave, and the distance between the nodes and the transverse speed. So the first thing we can kind of recognize, we'll write down, is the general standing wave equation we derived in an earlier video. So the standing wave equation looks like y1 plus y2, or this resulting sum, which is called y prime x of t, in general is 2 times the amplitude of each individual wave that has identical amplitude a, that has identical wave number k, therefore wavelength lambda, and frequency omega, angular frequency omega, frequency f. And so recall that this is the amplitude term, and this is the oscillation or oscillating term. And we can tell from the equation we're given what the amplitude term looks like and what the oscillation term looks like. So from that we can gather what the amplitude, for example, must be of the two waves that are identical whose superposition gives this oscillation. For example, if this quantity 2a is equivalent in our given equation to 0.5 centimeters, that means that a must be equivalent to 0.5 divided by 2. That's the amplitude of each individual wave, or 0.25 centimeters. For the speed of the two waves, well, speed is found from f times lambda, which another way to write is using the more common angular frequency and wave number, omega over k, which we can read off directly from the equation. Here omega is given to us as 40 pi radians per second, and k is given to us as pi over 3 centimeters per centimeter rather. And in this case then we can just use this basic calculation. V equals omega over k, and we will get here a result of 120 centimeters per second, 1.2 times 10 to the 2 centimeters per second. And in the next part we are looking at the distance between nodes. Well, the distance between nodes is always equivalent to half a wavelength, the same as the distance between antinodes. So any two consecutive nodes on any standing wave has this difference. And so what we need is the wavelength, from where we can use the wave number k. K is equal to 2 pi over lambda. So lambda is 2 pi over k, which we have, pi over 3 seconds or centimeters to the negative 1. And so lambda over 2, the distance between two nodes, is just 2 pi over k divided by 2, or pi over k. So the distance between nodes, let's call it d, is equal to pi over k, or pi over 3, which is equivalent to 3 centimeters. And so we have so far the answers to the first three parts, and the last part, what is the transverse speed of the particle of the string at the position x when t equals 9/8 of a second? Now, here we want to realize that, again, with any standing wave, there is an oscillation term, right, of the oscillation of any point, and it doesn't have to be a particular antinode there. Any point is oscillating at a particular speed and at any given time. And that's given by this oscillating term, cos omega t. So the position is fixed, x equals 1.5 centimeters, and we want the maximum transverse speed at that position. So all of the amplitude term here remains constant. And so the 2a sine kx, which we'll write down here, is fixed for a fixed position x, since k and a are also constants. So what we want is to get the maximums, not the maximum speed, the speed at a particular time. So we get this general expression by taking the derivative of this function of the position y dt and keeping the term, the amplitude term, fixed or constant. So what we get is, since we'll just have this fixed amount of the amplitude term, now we take the derivative with respect to t of cos omega t. And we've done this before, and we see that we get a negative sine omega t times the derivative of what's in the function, omega. Right? So we get negative 2a omega sine kx. All of that is fixed. And derivative of cos omega t becomes negative sine omega t. And now we can plug in the value for the values for the quantities of k and x and omega for x and t. So when x is equal to 1.5 centimeters and t is equal to 9/8 of a second, as the question asked us to look at, well, what you end up seeing is that this velocity term becomes, at those particular values, becomes 0. And the reason is that the term, which you can check for sine omega t, the oscillating term, when omega, since omega is 40 pi radians per second times 9/8 seconds, will give you sine of an integer number of pi, which is equal to 0. So really it doesn't matter what these other constant terms are, that oscillating term at that particular position has a velocity of 0. It actually tells us it's at one of its, therefore, maximum or minimum spots.